Hello everyone, this is Dr. Mohammed Hamdan. I'm a professor in mechanical engineering, and today I'm gonna give you a workshop on EES, how to use EES to solve an Otto cycle using cold air assumption. So if you are analyzing Otto cycle, this is one of the common problem you will see in thermodynamic, which is a gasoline cycle. We call the ideal one Otto cycle. In this example, we have an Otto cycle which has a compression ratio of 8, maximum temperature of 627 degrees C, and the beginning of the compression stroke, the pressure and temperature of the fluid are 100 kilopascal and 27 degrees C. Based upon the cold air assumption, determine the following. We have four points to find, which is the specific heat added to the cycle, the efficiency of the cycle, the specific work produced per cycle completion, and finally plot the efficiency versus compression ratio. EES will be very good tool, especially for point D here. So the cycle on a PV diagram will look like this: 1 to 2 compression isentropically, 2 to 3 constant volume heat addition, and 3 to 4 isentropic expansion where we get work out, and then 4 to 1 where we have heat rejected at constant volume. Now to solve this on EES, what I will do, I will copy the problem and go to EES. I have EES open, so here is my screen and I'm gonna write it here. Now first thing, I will go to option preference and change the size of text to 24 so it look bigger. And another thing I'm gonna do, I'm gonna comment this. So I'm gonna do this wiggly brackets and here. So now this is the text. You can see now turn to blue. This is a text will not be read as a command line. Now to analyze Otto cycle, we know that there is main 4 points. So we need to write these points as temperature and analyze it. First thing we need to add is the constant K equal 1.4, which is the specific heat ratio. Another thing that we would like to add is the compression ratio, which is R equal, R equal 8. So now I define 2 parameter, and next I'm gonna start adding point by point. So let's say point 1, and I know at this point temperature at 1, and temperature at 1 is equal 27 plus 273 because we solve everything in Kelvin. At point 2, what do I know? At point 2, I know the process from 1 to 2 isentropic, so if I want to find the temperature at 2, I know it by knowing temperature at 1 multiplying by the compression ratio of R to power K minus 1, and this relation we get it from the isentropic relation. So the process here is isentropic from 1 to 2. Now point 3, it was given in the exam or in the problem, which is T3 in the example. T3 is equal, if you read the problem, it's 627. So this is 627 plus 273, so we can write it in Kelvin. And finally, point 4. Note the notation I put in the beginning and at the end just to make this is text. So T4 is actually equal. I can know it by knowing T3 and using the isentropic relation for constant specific heat at T3. So it's T3 multiplied by 1 over R, multiplied by 1 over R to power K minus 1. And this relation, by the way, we get it from the equation sheet. So now we know the 4 temperature. I can find, for example, Qn. Let's check firstly if everything look fine. Yeah, we have 6 equations with 6 variables. Everything look good. So now I can say, for example, Qn is equal CV multiplied by, now Qn, we add heat between 2 and 3, so it's T3 minus T2. Now, CV is unknown, so to find it, the good thing here, we do not need to go to a thermodynamic table. We can use the function information. All the property are stored here, so you go to thermodynamic property, then air as fluid, and CV. Here is CV. So just say paste, you will find the CV, and this is C underscore V. CV at temperature, and now since we're using cold air assumption, this temperature will be room temperature. So we found Qn. Also we can find Q out, which is Q out, which happen between 4 and 1, which also I can write it as, I can copy this, so here CV, but it happened between 4 and 1, so I can write this as 4 and this is 1, T4 minus T1. Now I found Qn, Q out. I can calculate efficiency. Efficiency is eta, which is equal 1 minus Q out, let's write it, Q out over Qn. If I want to find work net out, I can get it from the efficiency definition, which is, yeah, let's write it as eta equal work net out over Qn. Now let's check our solution. We have 11 equations with 11 variables. That's really good. Now we can solve. So you can see it solve. It says there is only one potential unit problem. We didn't check units. Efficiency here is 56%. Let's check the unit first. So to check units, we go to option, unit system. Make sure here the temperature in Kelvin, unit system is I, mass in kilogram, pressure in kilopascal, and energy in kilojoule. So this is look okay. Now option, variable information, or you can hit F9. And here you can see all the variable you have, which is the 11 variable. The unit of CV, let's say it's kilojoule per kilogram Kelvin. I will just write kilojoule per kilogram. I know this is not correct, but I'll show you how EES can help me to detect such mistake. Eta doesn't have unit, K doesn't have unit. Qn is kilojoule per kilogram. Q out is kilojoule per kilogram. R doesn't have unit, the compression ratio. Temperature is in Kelvin. So I'm just gonna type Kelvin here, and work out is kilojoule per kilogram. So hit OK, and now I can solve. Now when I solve, it says there is 3 potential unit problem were detected, and if you go and check, you're gonna find that it says Qn it has a unit of kilojoule per kilogram, while the right side here has kilojoule per kilogram Kelvin, which means CV was not given correct. And similar for the Q out here. So to fix it, I can go to variable information and make sure this is kilojoule Kelvin. Kilojoule per kilogram Kelvin. When I hit OK and run, you will see no unit problem were detected. So also show the units here of my solution. So now we can calculate the now is next point that we would like to find the part D, which is plot the efficiency versus compression ratio. To do that, to plot the efficiency versus the compression ratio, we're gonna put compression ratio as comment. So now if I try to solve, it will tell me I have 10 equations with 11 variables. It cannot solve because we commented the variable R. Now what we will do, we're gonna create a table, we call it a new parameter table, where R, we're gonna plot it with efficiency. So here is eta. So now 2 variables in this table, and we have 10 runs. So here's 10 runs. Now we'll fill the value of R from, let's say, 1.001, because it can solve from 1 to 20 compression ratio, and I'm gonna use let's say log spread, so it will give value from 1 to 20, and if I want to calculate efficiency, I don't need to do it one by one. I just hit here run, and I'll get the value for the efficiency changing between 1 and 20. If I want to plot this result, I can go to plot, new plot, XY plot, and now I'm plotting in XR, and in Y, I'm going to put in Y axis, we have eta. If you plot it, you get this figure. This figure is, we always show this in term 1, showing how the efficiency of Otto Cycle changed with compression ratio. So here I'm going to stop, and next video I'm going to show you how to use variable specific heat to do or solve the same problem. I hope this is clear. Wish you all the best. If you have any question, please write it down in the comment.